So hello and welcome to another podcast from the Engineering Department at Durham University. As always, my name is Chloe and today we are joined by Will Coombs, who is a professor in the department. Welcome, Will. How are you?
I'm okay, thank you. A little bit tired. I've got a 7-week-old at home now, so that's kind of keeping me busy outside of work and a little bit sleepy as well.
Oh, okay, so today we're hoping to talk a bit about your experiences at Durham, both as a student and now as a professor. And then we're going to talk about postgraduate research admissions, as I know you're involved with the research degrees offered by the department. So to start at the beginning, I believe you completed both your MEng degree and your PhD here at Durham. Why did you choose Durham?
When I was, in that situation as being a sort of a 17-year-old, I'd done a number of years of work experience working with a civil engineering consultancy in the lead up to going to university. And so I kind of knew I wanted to study engineering. I was pretty sure I wanted to study civil engineering. And I did the usual thing of visiting various universities and looking at courses, etc. Back in the days when you used to have to write to universities to get them to send you a prospectus. So things are a little bit simpler now. And the thing that really made me want to come to Durham is I just really enjoyed the open day visit, the open day experience. And that, I suppose, sold to me the idea of coming to Durham. Also, I grew up in the southeast, so I wanted to move a reasonable distance away from my parents, as I can sure many students relate to. And the other thing that appealed to me was actually I spoke to one of the directors of the company that I worked for, and he had gone to Durham himself, and he found that the general engineering nature of the degree had been really beneficial in his career, particularly as he advanced. He found he was able to coordinate and lead teams more effectively because he understood a little bit about all the engineering disciplines from that general background. And so that's really why I chose to come to Durham as an undergraduate student, and I basically never left. And the reason for that is, as I went through my degree, I was sponsored by this same company that had helped me beforehand. And I basically had a job lined up when I left, and it suddenly dawned on me one day that I was going to be bored going to work for that company, or there's a risk of being a bit bored. And it was kind of fortuitous that when I was starting to have those feelings, that one of the professors in the department was advertising a PhD position. It looked very interesting to me, and so I decided to pursue a PhD in the department and continue my time at Durham University. Again, thinking I'd definitely leave and go into industry when I finished my PhD, but it's funny how things change.
I think that's quite a common story with some of the professors in the department kind of coming and never leaving. So for your MEng degree, what area did you choose to specialise in and why?
So I went into civil engineering. I specialised after those 2 years. I mean, the degree structure back then, I first came to Durham 17 years ago, hasn't actually changed a huge amount. Obviously the content has evolved, but the basic structure is the same. So after those first 2 years, I specialized in civil engineering, and it was what I thought I was going to specialize in before coming to university. And it was actually just the area that interests me the most still. I was open to change, but yeah, I was really interested in the civil engineering topics and area, and so decided to pursue that direction. It's also interesting, at the time, the department had around 140 students per year, so not too dissimilar to what it has been for a number of years, although we're growing now. And actually, of those 140 students, 50 to 60 of them chose civil engineering. So there was a really big cohort of students that wanted to do civil engineering that year. And it's interesting how that's changed and kind of fluctuates over the years, that sometimes you only have 20 doing civil engineering and 50 doing electronics. Back when I was a student, only 5 to 10 students were doing electronics. So I wasn't following the crowd, but it's just the area that interests me the most. And it's also an area that I felt that the academics, the lecturers in that area were really inspiring and really clear. And I kind of had confidence that they were going to give me a really good education in that area.
Oh, that's really good. Yeah, and I guess that's one of the benefits of the general course. You can you kind of, even if you've got an idea of what you might want to specialize in, you have a bit of time to decide after experiencing some of the engineering if that's what you do want to do, or whether you are open to doing something different. So that's really good. So
it is something that I do see students change as well as they come through the degree. I always ask students as they come in, that act as their academic advisors, what they think they're going to want to study in their third year. And for many of them, it stays the same. For a lot of them, though, it does change. It evolves as they learn more about the disciplines and they get really inspired about something. And they can come in thinking they wanted to be a mechanical engineer and end up specializing in electronics. And I think that's a great thing about our degree. And there are obviously lots of other degrees around the country that offer that flexibility. But really, when you're 17 looking at applying to university, you don't want to commit yourself for almost the rest of your life in terms of your career pathway based on your perception of the disciplines from that point. I think it's great to have that time to think about it and learn about the subjects. And in my case, I didn't change, but a lot of people do.
yeah, no, that's very true. So can you tell us a bit about the research you undertook for your PhD?
Yeah, sure. So my PhD was all about understanding the behavior of soil. Now this, for a lot of people, perhaps when you look at soil as in mud, dirt, depending on what you want to call it, you perhaps think it's quite a simple, relatively simple material, but trying to represent the behavior. And when I say behavior, I'm particularly thinking about stress strain or sort of force displacement behavior of soil. It's actually very, very complex, and in a lot of ways far more complex than a lot of the other engineering materials that we typically use, such as steel and concrete and other materials. And it's complex in the nature of its behavior, but it's also complex in the variations that it has. A lot of engineering materials we use are very carefully controlled in terms of quality, whereas when we're dealing with soils and we're building upon them in the ground, we don't have that same control. We can sample them and understand that variability, but there's a lot more uncertainty. And my PhD was all about developing models to represent the stress strain behavior of soils, or force displacement and behavior, for those of you that are less used to these concepts of stress and strain. And particularly developing models that were suitable for problems that involve very large deformations. And that's something, again, which is quite unusual in the area of soil mechanics and geotechnical engineering, in that we subject these materials for very, very large deformations. So, for example, if we're installing foundations, deep foundations such as piles, we can be displacing these soils by huge amounts. And so we need to be able to represent their behavior under these very large deformations. And I've kind of continued with that line of research, but I've also expanded into different areas. And during my PhD, I developed both very simple models that could be perhaps used by practical geotechnical engineers, but also much more complex models that are perhaps far more sort of academic or research really tools, I would say, to represent the behavior of soil.
Sounds very interesting. And so I think we've touched on the reasons a little bit earlier, but what led to your decision to pursue a career in academia?
I suppose at the end of my PhD, I still had lots of questions that I wanted to investigate and answer. And I felt that if I went into industry, I wouldn't have the opportunity to pursue and answer those questions that I was still interested in. And again, it was a little bit fortuitous in that when I was coming towards the end of my PhD, there were academic positions opening within the department that were aligned to my expertise and interests. And I also had sufficient journal publications already behind myself from my PhD research that I was in a position to actually go and apply, and I was successful in securing a lectureship position out of my PhD, which is a little bit unusual. Most people do a paid researcher position after their PhD before then looking for an academic position. But I suppose in my case, things just aligned well in that my background expertise aligned with the direction of the department that it was going in terms of its growth strategy at the time. And so I wanted to pursue that academic pathway to provide really myself with the freedom to investigate the things that interest me. One of the really nice things about being an academic is you're very much the kind of captain of your own ship, and that you can steer your career pathway to look at those questions and problems that are of interest, provided you can secure funding to do that and find good PhD students to pursue those directions. And I just felt I wasn't going to have that same flexibility if I went into industry.
Yeah, no, that sounds like really good reasons. So looking at your current research now then, I believe your research focuses on sort of areas of computational mechanics. Can you expand on this and tell us a bit more about your current research?
Yeah, sure. So before maybe going into actually what I research into, maybe people are not entirely familiar with the term computational mechanics and really what that means. And the basic idea of computational mechanics is, as a field of research, is we use computational or numerical methods, so methods that are implemented into computers, to study problems that are governed by the principle of mechanics. And these can be in lots of different areas. So you could be studying problems in fluid mechanics, in solid mechanics, which is the area that I specialize in electromechanics. Really anything that's governed by basic laws of mechanics falls within this realm of computational mechanics. And what you find is, as an engineer, when you're looking at problems, in a lot of cases, if you have a simple problem, there is an analytical or a closed form solution, something that with a piece of pen or pencil and paper, you can write down and work out a solution to that's a reasonable approximation to the problem that you're studying. But you'll find that as things become more and more complicated, there's no longer those analytical or closed form solutions to solve your problem. And you have to resort then really to numerical methods that include these basic laws of mechanics to then analyze a problem with maybe a more complex geometry or more complex loading, etc. So all of my research is within that realm of computational mechanics. I don't really do any experimental work in my research. And the areas that I'm now looking at, I still pursue this avenue of understanding soil behavior and developing computational models to represent soil. But more and more, I'm moving towards looking at the bigger picture in terms of the overall response of a physical problem. A common theme in all my research is that they're generally problems that are difficult to tackle with commercial software. So I'm not really interested in using commercial software tools. I develop my own code, and my students develop their own code and software within the department. And we go after problems that just can't be solved with commercial methods, or just don't give you very good results with commercial methods. And that can be due to them involving very large deformations. So a lot of my recent research has been focused on offshore wind energy and the geotechnical aspects of offshore wind energy. So perhaps something that many people don't think about is when you deploy an offshore wind farm, somehow you have to transmit that power you're generating, or energy generating, back to shore, and that's done via a cable. But we don't just lay that cable on the seafloor. In order to protect it, we tend to bury it a certain distance below the seafloor. And the way that is done is using a giant plow, basically, just like you would plow a field. They look slightly different. They're basically like a giant knife blade, which you slice through the soil and you install the cable behind. And trying to model that process of dragging a plow through the seabed when you have different soil behavior is a really challenging computational problem that commercial methods really just can't solve, or can't solve in a very effective way. So that's one example of the sorts of problems I'm trying to tackle. And the engineering question there is, from someone trying to deploy one of these cables, is how fast can you drag that cable? What are the forces involved in pulling that plow across the seabed? Because that then dictates the size of the vessel you need, how many days you need that vessel for. And these vessels cost hundreds of thousands of pounds a day in some instances. and providing more information in those sort of areas is where I've been really focusing my research efforts in recent sort of years. One area I'm moving into more and more, though, is modeling fracture. So fracture and failure of engineering components. And not just engineering components, an area that I'm really interested in at the moment is modeling fracture in ice and understanding fracture potential in ice and how that's influenced by changes in climate as well. So looking at glaciers, looking at events like iceberg carving, where large pieces of ice carve off glaciers, and really trying to use the computational tools and methods I'm developing to perhaps answer some or provide ingredients for some of these bigger questions that we have at the moment to do with rises in sea levels, understanding how much of the ice is going to change over the coming years, etc. And fundamentally understanding the small scale kind of physical processes that are going in and going on as the ice fractures. So that's just kind of a flavor. I've got lots of different areas I'm interested in, but those are a couple of examples of things that I'm looking at the moment.
Yeah, no, it's really interesting. And it's really interesting to hear how you can link sort of traditional, I guess, civil engineering into some of the world's current problems with sort of integrating renewable energy sources and looking at the more extreme environments with sort of ice and things. So it's really interesting. So in terms of when you're a lecturer, what modules do you teach?
Okay, I've taught various things over the years. At the moment, I teach a third-year course on the finite element method, which is really the computational method used in industry by engineers to analyze certainly solid mechanics problems. It is kind of the tool, and so it's really important that students, I think, have a knowledge of how that method works. And then in the fourth year, I teach a module on nonlinear solid mechanics that's also taken by MSc students, and another module on aircraft structures, which may seem a little bit strange given I'm a civil engineer by training, but really kind of structural mechanics is structural mechanics, and it doesn't matter if you're designing a bridge or an aircraft, just kind of your design constraints are a little bit different. But I've also taught in the past modules to do with soil mechanics, land surveying, all sorts of different things over the years, but that's what I currently teach.
That's great. So if we move on now to talking a bit about postgraduate research degrees, can you give us an overview of the MCR and the PhD degrees which the department offers?
Yeah, of course. So just to explain my role in the department, so I'm the Director of Postgraduate Research, which basically means I have overall responsibility of our research degree provisions within the department. It doesn't mean that I supervise all of the students because they'll be supervised by academic teams in the particular areas, but I kind of have that general oversight for our degree provisions in this area. And an MSc by research is typically a one-year program. If you were to do it full-time, or a two-year program if you do it part-time, where you'd be working with an academic team, typically two supervisors, to investigate a particular problem that is of interest both to the student and the academics. And basically over that year, you write a dissertation. There are no examinations. You don't have to sit at any formal taught courses. You spend that entire year pursuing your research direction and then writing a thesis, which is typically somewhere to 50 to 100 pages long. A PhD is very, very similar, but normally our PhDs are 3.5 years long if you're doing it full-time, or 6 or 7 years if you're doing it part-time. But instead of just spending a year on your research, you spend that full 3.5 years of time, again, working with a pair of academics as your supervisors. Often also there may well be external parties, such as an external company that's interested in the research or is supporting the research in some way. And you're focusing entirely on that problem. And again, there are no taught courses. You do have certain reviews. So you're checked by academics that are outside of your supervision team as you progress through your degree. But provided you pass those reviews, then the idea is you continue with your research, and hopefully at the end of that 3.5 year period, you submit your thesis, and then you're examined in order to obtain a PhD and become a doctor. They're quite in a lot of ways, they're quite it's very different to taught studies, because with taught studies, you have these deadlines, this very sort of strict structure. You have these lectures you go to or don't and catch up later. But anyway, you have set points where you're going to have exams, set points where you're going to have coursework. A PhD, a research degree, is nothing like that, really. And you have to really want to pursue and be determined to pursue your research, because you've got to set your own goals, your own agenda. Obviously, you've got academic supervisors to help you with that, but you've got to drive the research forwards. And some students thrive with that, and I think some students really struggle with that change from that very structured course to suddenly a very open-ended problem where you have to set your own deadlines.
Yeah, no, it sounds like completely different to sort of what I'm used to, for example, but very interesting. And so thinking about those differences then between taught studies and kind of research, what does a typical day look like for students on these programs?
Very varied, I guess, really, is probably what I'd say. It depends on the nature of the PhD, really. So some, for example, students that are working with me would be doing projects that are theoretical and computational. And so they might be spending a lot of their time reading papers, trying to understand methods, developing and driving their own methods on paper or in electronic notes, and then implementing those methods in code, and then trying to generate results, checking their results are correct, etc. They'll also be spending time, meeting up with other PhD students. We've got a body of around 120 research students within the department, and we organize department-wide activities, such as there are coffee mornings every week where students get together and meet and discuss their ideas. We have an active seminar program, again, where students present their research and what they're doing to other students within the department to try and generate this kind of cross-collaboration and make other people aware of what's going on. Also, a lot of our students help with demonstrating in our undergraduate labs. And if you're a student at Durham, you've probably experienced this, where you've been helped by a PhD student who's an expert in that particular area. In terms of then, if you're doing an experimental PhD, you kind of replace that computational method development and implementation with experimental method development and actually execution. And what you often find is you spend weeks and weeks and weeks and weeks and nothing really works. You're constantly trying to get your method to work, etc., etc. And then finally, your method works, and then you can start to actually generate useful results. And I think that cycle of things not working is typical of any PhD, be that computational or experimental. And so it's very important to have that perseverance and knowing that if you keep going, things will work, or you'll get to the bottom of why they don't work. But days can be very varied. And actually, I found my time as a PhD student kind of the best time I had at university, because you have a lot of freedom to explore and read what's of interest to you without that pressure of the next piece of coursework, the next lecture, etc., that you have in a taught program.
Yeah, that's great to hear. And I think the freedom is something that definitely attracts a lot of students. So how would students go about applying for these programs?
So the most important thing first is to really work out what area you'd like to do some research into, because you've got to be committed and really interested in that area of research. If you're not going to be successful at a PhD. So it's thinking about what areas of engineering interest you. And then the next stage is trying to identify suitable academic members of staff that can supervise a research project in that particular area. So many students kind of get inspired by their dissertation projects that they do in their final year of their degree, and then perhaps start a conversation with that academic supervisor about perhaps extending that dissertation project into a research degree. And that's quite a good way to go. But it's key that you start that conversation first between yourself and an academic that could potentially supervise your research, because you may well have a kind of what you think is a great idea, and I really want to research into this. You go and talk to the academic and say, oh, that was done 30 years ago by these people, and there are no real questions there anymore. But then they'll be able to say, but the current focus is on this, and does that interest you? It's having that conversation, dialogue with an academic that has much more experience than most students would have in the area. They should be a world-leading expert in that area and can help shape and develop a research proposal that you would need to then look at applying for a PhD. And that's really the first step, is to develop that research proposal and idea. And that could be with academics at Durham or academics anywhere around the country or around the world. And then once you've got that idea, then that's the point to look at actually applying to the university that you're interested in applying for. And often that application process does require quite a lot of information. They'll require a research proposal, which hopefully you've developed. They'll require a personal statement. Maybe that fills a lot of people with dread in terms of thinking of UCAS personal statements. It's a bit different. You're kind of expressing why you want to do a research degree, but you don't have that same character limit that UCAS imposes on that writing. You need to have references, and as well as completing an online application form with some basic information, and then that will come to the department, and typically then the academic would interview the student. And again, on that application, you would be asked to indicate an academic supervisor. And that's why it's really important to have that conversation first, so that they're expecting your application. And then if an academic offer is made, that's kind of, you've then got an offer for a position to study at the university. But a completely separate thing is how you fund your studies. So unlike most taught degrees, for research degrees, certainly in engineering, you normally don't pay yourself. So you wouldn't normally pay your fees, and you would normally be given a stipend of around £15,000 per year, tax-free, in order to support yourself as you complete that PhD. So the vast majority of PhDs in engineering are funded, and they're funded through various different means. The department and the university have a number of scholarships that they offer. There are other centres around the country that have funding to support PhD students, etc. So if anyone is thinking about doing a PhD, don't think that, it's going to be another 4 years of student loan and debt, etc. You should be looking for opportunities for funded PhD positions within universities, and that's the norm if you're studying for a PhD in engineering. And £15,000 doesn't sound a lot, but it's tax-free. You can supplement that through doing demonstrating work where you're paid by the university, etc. And certainly in a city such as Durham, it's ample to live quite comfortably, certainly compared to maybe undergraduate study.
Yeah, no, that's really helpful information. So can you give us some examples of research that students have undertaken recently?
Yeah, sure. Obviously, we're a general engineering department, so it's really, really diverse. But there have been projects related to things like how you stabilize earth and materials so they can be used in construction, and doing that with different methods. There's been projects, the sort that I supervise, where they're looking at developing computational models to understand fracture problems or soil mechanics problems. There are other PhDs more related to electrical engineering, where you're looking at stability of power systems, power networks, etc. Projects on the electronics side, looking at things like the next generation of photovoltaics, looking at flexible electronics, printed electronics. Also thinking about more aerodynamic or mechanical engineering applications, sealing of turbines, etc., etc. It's so diverse in the department, which is a great thing, actually. I think that they're really diverse projects, but there's also an awful lot of overlap between them, and students learn from each other. And I think probably the thing I'd say is, if students or prospective students are interested in the PhD research that's going on at the moment, is just to have a look at our web pages, and in the staff area, all of the PhD students are listed, and they should all have their own profile description of the research they're doing. And that will just give you a flavour of the sorts of things we're doing at the university in different areas.
Yeah, that's great. And so finally, to finish off, out of all of the experiences you've had at Durham, both as a student and as a professor, what has been your favourite experience?
Am I allowed to have one as a student and one as a
Yeah,
academic?
sure.
Is that okay? I'd probably say that as a student, my best experience was the involvement that I had with the University Canoe Club over 4 years. So when I was a student, I was very active with the club, competed with the club at university level, etc. And the friends that I made during that time, have become lifelong friends. They're still friends now. We still meet up, etc., etc. Unfortunately, I don't do as much kayaking as I perhaps used to, but I think that that was really one of the highlights of my degree, even though it wasn't part of my degree, but just that network that of friends that I made during my time as part of the University Canoe Club. For people thinking about applying to university, it's a really important thing. You can find a course you think is great, but if you don't like the overall environment of the university, you're not going to have a fantastic time. And it's those kind of added value things that really make your time at university. And then as a academic, I think one of the most satisfying experiences was seeing my first PhD student graduate. And then what I mean is a student that I kind of took in as from the beginning and saw them all the way through the process, and then they graduated 4 years after they came to university. And that was a really satisfying and kind of proud moment for me, really, in terms of I'd been there myself a number of years ago, but then being able to help someone else on that journey through a PhD and achieve what they wanted to do in their research. That was a really satisfying kind of experience. And I suppose that's what really motivates me as an academic is helping other students to develop within both the taught curriculum and also in their research, and then leave and go on to do other things based on using the skills they've developed within their time at Durham University.
That's really lovely to hear. So thank you so much for joining us, Will. It's been great to hear from you. And thank you to everyone who's been listening. We hope you've enjoyed this podcast. As always, be sure to keep an eye on our social media pages for future episodes and for news about our department.
Okay, thank you very much.